Hi everyone, welcome to this session. So my name is Anuj and today I'm going to talk about our work on advancing data integrity in Linux. So it is mostly about what modern storage hardware offers and what is the gap in how the operating system consumes it. So here is the outline of the talk. First I'll talk about the current data integrity stack and what is missing, and then I will talk about our three main contributions, which is the flexible PI, IO-Uring PI interface and file system managed PI. Then I will also share some of the evaluation results from the experiments that we did on BTRFS and XFS, and then I'll conclude the talk. So what is protection information or PI? So it's basically a metadata tag that gets attached to each data block and helps in detecting corruption. It travels along with the data and it helps in enabling the end-to-end data protection. So there are two kinds of PI. One is the def, where the PI is interleaved with the data and it creates memory alignment issue. And then there is DIX, where the PI is stored in a separate buffer, and Linux supports DIX. So how does PI structure looks like? So there are three tags. First is the guard tag, which is the checksum of the data block. Then there is the application tag, which is an app defined value. And then there is reference tag, which is a logical block address, and it helps in detecting the misdirected writes. Based on what the device decides to check, we have 4 different PI types. So in the type 0 PI, the device decides to check nothing. In the type 1 and type 2 PI, the device checks the guard and the ref tag. And in type 3 PI, the device only checks the guard tag but does not check the ref tag. So this is how the existing data integrity stack looks like. So the support is there in the block layer and it supports the DIX model. File systems are unaware that the underlying device has this capability, and most of the handling is done at the block layer level itself, and only in-kernel components have the ability to attach the PI. So these are the gaps in the existing data integrity stack. On an application level, we have no user space interface. So applications who would like to send the PI along with the data, they cannot do it. And vendors who would want to have this kind of ability would be forced to build the custom kernel modules. Then file systems are unaware of the device integrity feature and they end up implementing redundant checksumming. And at the block layer, not all PI formats are supported. So coming with the first contribution, which is the flexible PI support. So the problem here is very simple. NVMe devices can place PI either at the start or end of the metadata buffer, but Linux assumed that PI will always be placed at the start of the metadata buffer. So this breaks compatibility with the device formats where the PI is at the end of the metadata buffer. So the solution is flexible PI. We introduce a new field, which is the PI offset, and it gets set by the driver during the integrity profile registration. It basically tells the block layer that where the PI starts within the metadata buffer, and all integrity operations will start using this PI offset. As a result, now the block layer can handle the devices with the different metadata formats, and this support has already been merged into the 6.9 kernel. Coming with the next contribution, which is the IO-Uring PI interface. So the motivation here is that the block integrity support in the Linux is restricted to the in-kernel IO paths. Application who would like to send the PI along with the data cannot do it. And if we want to achieve full end-to-end data integrity, then we need the application involvement too. So we decide to implement this interface using IO-Uring. IO-Uring because it's the most efficient async IO interface in the Linux, and it also allows us to add the support without creating any syscall bloat. So IO-Uring design involves having 2 ring buffers, which is a submission and completion ring buffer. Application prepares the submission queue entry and places it in the submission ring. Kernel fetches the SQE from the submission ring and processes based on the specified opcode. And after the processing, the completion is posted as the CQ in the completion ring. So the first design that we came up with, we stored the entire PI information within the SQE. And of course, that was not a very good design choice because it bloated the size of the SQE. So then we moved to a more extensible approach where we prepared the PI information in the user space and passed it as a pointer in the SQE. So what it helps is that it makes it future proof, and new features and attributes that get added down the line can reuse the same pattern. So applications can now submit the PI along with the data, and if they wish to do so, they need to prepare this new structure IO using ATTR PI in the user space. It has the following fields: the flag field, which determine like what are the integrity checks that you want to do on the PI buffer. Then you have to specify the length and address of the PI buffer, and then you have to specify the seed value for the ref tag remapping and app tag for the application tag value. So this interface helps application to control the protection semantics, and this support has been merged in the 6.14 kernel. Here is a simple example program, and it shows how simple it is to use this interface. Application just has to prepare the PI and then populate all the information in this structure, and then pass this structure as a pointer to the SQE and submit the IO. Then our last and the most important contribution, which is the file system managed PI. Most of the heavy lifting and core plumbing for this was done by Christoph, so thanks for that. So the problem that is there is that block integrity starts too late. So it gets applied when the file system layout and transformation has already been done. So any corruption that gets introduced during the file system processing gets missed. So with the FSPI, the attempt is that we extend the protection envelope and we generate the PI and generate and verify the PI in the file system itself. With this, we are able to catch the software induced errors much earlier in the IO stack. So let's discuss a few aspects of the design of FSPI. So one of the powerful aspect is how we handle the different PI types. So for PI type 1, 2, 3, where the device will actually verify the PI buffer, both the file system and device needs to compute and verify the PI. And the checksum algorithm in this case will be determined by what the device format supports. With the PI type 0, we get a little bit more flexibility to play with. So the file system will generate the PI, but because the device is not going to check it, so we get a bit of flexibility in deciding what the checksum algorithm we want to implement. So for example, the file system can choose to use the CRC32, which is generally not supported by the hardware. Then we add the helpers for the FSPI in the block layer so that any file system that wants to add this ability can make use of it directly. And then we also do some optimizations for the file system metadata. File system metadata is already protected, so FSPI skips the PI generation and verification on metadata to avoid the redundant integrity work. So the first candidate that we choose is BTRFS. So BTRFS is actually a great candidate to implement FSPI. So BTRFS actually uses out-of-place checksum trees to implement the checksumming. So checksums get stored separately from the data, and every data write will result in updates to multiple metadata trees. And the problem with that is that it causes a lot of extra writes, which lead to write amplification and increased CPU overhead. With the FSPI, BTRFS will be able to avoid the usage of the checksum tree and move the integrity metadata next to the data block as PI. And we will be able to use the device enforced PI instead of the checksum tree. So this would work both for the direct IO and buffered IO. PI would be generated and verified by BTRFS, and because there is no checksum tree, so there would be no checksum tree updates on the writes. So BTRFS has redundancy and recovery support, But for the FSPI, this is still a work in progress. So in case there is any checksum mismatch, then we just return an IO error to the application. Next, we choose XFS, and XFS is a bit different than BTRFS because XFS already has the metadata checksumming, but it lacks the data checksumming. So FSPI provides a good way of adding data checksumming to it without changing the on-disk format. PI generation and verification is added into the generic IO map path. And since XFS has no data redundancy, so any corruption that gets reported is sent back as an IO error. Christoph has already sent the patches for adding the XFS PI support in Linux, and I think there is good response to that, so I think we should get it upstream soon as well. Then I will share some of the evaluation details that we did for the BTRFS and XFS. Because of the lack of space and time, I have kept it short, but you can refer to the paper for the complete evaluation details. So we use a FIO workload, the workload details are given, and the setup details are also shared here. So for BTRFS, we measure the write amplification performance and CPU utilization for the base and the FSPI case. In the base case, the BTRFS would be using the checksum trees, which will add the write amplification and other kinds of overhead. And in the FSPI, we would be using the device PI feature, so those kind of overheads won't be there. So for the write amplification, we use FIO to write the same amount of data from the application. And then we measure the number of host write and NAND writes. And we see that there is a steep reduction in the host writes and the NAND writes for the FSPI case as compared to the base case. So yeah, it helps in reducing the write amplification overall. Then we also compare the performance and CPU utilization, and we see that there is the most benefit in the case of random write workload because it suffers the most degradation from the rendering tree writes. So and for the other kind of workloads, the performance almost remains the same with the base case. Then we also do some evaluation on the XFS side. So in case of XFS, we are adding the checksumming ability to a file system that does not have it. So we expect to measure the overhead of adding the checksumming, and we do the performance and latency numbers for that, and we see that there is a small but predictable overhead for the case of XFS. So concluding the talk, I think we are just trying to make rich use of a device provided feature in the kernel IO stack. If I summarize the main contributions, we do the flexible PI, which enables the broader NVMe format capability. Then we do the PI user interface, which makes the integrity metadata application visible. And we do the FSPI so that the data integrity gets extended from the devices to the file systems. For BTRFS, we are removing the checksum tree overhead, which results in the reduced write amplification and improved performance. And we are able to add the data checksumming support to a file system that lagged it previously, of course with a small and predictable cost. I think that will be all. Thank you.